Okay, everyone knows that reasoning in RL is the big thing right now. I've been trying to master the GRPO loss function, how it relates to PPO, and how it was actually implemented in the last few days. I think we'll get to this, but there's been a couple papers. I have them on the side here. One is Dapo, which was a very strong paper that kind of understands different ways of implementing this, and then these are code, and then this understanding R10 paper that have come out recently to kind of get me thinking on all of this and how GRPO should be done. So I'm going to kind of go through a whole bunch of things. I have a blog draft, a thread on Twitter, and these papers to start with to kind of talk about the story of GRPO, how it relates to PPO, and why people are so in the weeds on implementation details right now. The links to all these things that I'm showing are down in the description, so you can look at those if you want to do that. So GRPO is group relative policy optimization. GRPO is a variant of PPO where they change the advantage computation. It is from this 2024 DeepSeek math paper. So I'll kind of scroll down and get right into it. Where they have a bunch of results, but what they do in this section is they kind of show how this PPO loss function can be transformed into something called GRPO. To start, I'm going to go back to the left. We're going to just look at policy gradient and kind of understand this. And what policy gradient is doing is essentially trying to increase the likelihood of actions that have high rewards. And I think what we need to know here is what an advantage function is in language models. And an advantage is essentially the difference between the value you got for an action and the underestimated underlying value from the environment. So there's a lot of different things you can do here. I think why we talk about advantage is because advantage is what is used in PPO and therefore in GRPO. I think we can pull up a lot of different things on, I'm opening a can of worms here, but there's a lot of different things. I can go up to my definitions that should have it. So the advantage function quantifies the relative benefit of taking an action A in a state compared to the average action. Here you can see it's the difference between the Q function, which is action dependent, and the value of the state. So this is kind of what I said. You can just look at it more specifically here. And we go back and we load a PPO, and you see that what PPO has done is kind of derived this controlled step policy gradient relative to the advantage. You can see here that a core part of the PPO loss function is this ratio between the current policy parameters and what's called the old policy parameters. These old policy parameters are with respect to the batch that is being updated, not the KL constraint and kind of this RLHF optimization. So that can be very confusing. The default in PPO and GRPO is you take multiple policy gradient steps per batch. So that's what all this clipping is doing, is as you take multiple gradient steps per batch of completions and ratings, essentially PPO and GRPO constrain the step size, so to say. If you're a nerd about this, you can look into derivations of policy gradient, and you see that this ratio between the current policy and the old policy kind of falls out of the math, so to say. So if we go back to like what is actually PPO versus GRPO, there's an example in this DeepSeek math paper on the right. We're looking at figure 4, which essentially GRPO removes the need for a value model. Where the value model is normally used with what is called GAE, generalized advantage estimation, to compute an advantage. And GRPO just looks at different answers to a single question in the prompt, a simple prompt question. And these multiple answers are used to get a advantage estimate. And we can see this advantage estimate down here when the section outcome supervision with RL, where the advantage estimate is just the difference between an answer and the mean of this group. You can kind of see it here, where in PPO, you're learning a whole value function to actually do this. Some interesting things to note that we will come back to. When DeepSeek introduces this PPO loss, they're adding this 1 over O term, 1 over the magnitude of O, which is essentially a length constraint on PPO or GRPO. If we go into kind of the generalized formulation in the book on the left again, there isn't this kind of 1 over O term. I think what you'll see on the left is this 1 over G and the sum from I equals 1 to G. this is kind of summing over a batch or a sequence of samples in the batch, and then it's doing this sum across samples where it looks at the log ratio, this kind of probability ratio between the policy multiplied by the advantage. If we actually look at the implementation of policy gradient, the simplest way to think about a policy gradient loss function is that it's kind of this advantages times this ratio that I was talking about, where it's very simple. And it's really easy to kind of lose track of this. We're thinking about advantages times ratio and then kind of changing the step size as we're doing this. And if we go back to PPO as I scroll around, there's this clipping that essentially controls the step size based on different conditions. If the advantage is positive, if the advantage is negative, and then kind of this log ratio, which stays close to 1, which is why we're clipping just above and just below 1 on the log ratio. So you can think of this log ratio as just changing a little bit for different tokens, but there's a gap between the left and the right here, where the left doesn't have this per token sum and the right has this per token. And the sum from t equals 1 to O is kind of how you can actually compute the log probability for PPO or GRPO. Essentially, what we're doing is we're computing a loss per token. And if you have a probability of a sequence from a language model, you essentially have to sum across the probabilities from the language model. So each token has a probability, and if you take the kind of log of this, you're going to get a sum of probabilities. So that sum is kind of the sum from t equals 1 to O. You're looking at the probability of each token and weighting it relative to the advantage. What is interesting is that these default implementations have kind of got this length normalization term in there. I have a few of these open. So if you look at the TRL trainer, we're going to kind of see that this has, we have to scroll up to find the advantages actually. But yeah, we have you kind of just have the advantages, and then you unsqueeze them here on line 960. Let me zoom in a little bit. And then the loss is really just like per token loss times completion mask and stuff like this, which is really not that complicated. I think the coefficient here is the log ratio, which is the token log probs minus the old token log probs. So if you have the dividing factor of a logarithm, so a log of x over log of y is a difference. So that's what we're doing. If we go back to this loss function, so we have these two. When you actually compute the probability from a language model, you use log probabilities. So you kind of just end up with this difference here. So the actual implementation is really simple. So that's kind of what policy gradient is doing. If we look at the actual advantages we have to compute the group-wise advantages here on line 870 for GRPO, where we just have the rewards minus the mean of the rewards over the standard deviations. It's just this normalization factor within a bunch of prompts to get this to get the advantage. I think most of you watching this will probably know all of this, or I will have already lost you. And kind of some of the interesting things that came up, for one, was kind of this idea of how should we actually apply the loss in a GRPO setting. I posted this tweet that was kind of asking, like, what does it do to change from the RLHF setting where you have a penalty applied to the reward versus the GRPO implementation, which applies it to the loss directly. This kind of went downstream into a discussion of how we should actually compute the loss, and Dan Hahn of Unsloth kind of made this comparison of how we can sum the different losses. And the difference here is whether or not we're summing across each token or each completion. And we don't actually know which one is best, but this ended up coming up in a few of the other papers here. So what we can see here is the TRL loss, which is we take the loss per token, which we compute with policy gradient and then mask it, and then we sum them all together and we divide by the mask.sum. Mask.sum is just going to be the total number of tokens. So essentially this is just looking at the global mean across all tokens. And the second RLHF loss is masking them and taking the sum across the first dimension. And the sum across the first dimension is essentially we're going to average the losses per response, so kind of per completion, and then average them globally. And what you can see is that these two things create different losses. I could show you that in a kind of soon to be merged example in my book. It has the same thing. You can kind of think about this as if there's one token very different in both of these losses, then if you average them in different ways, you're going to kind of get different loss functions. And this is what Daniel's talking about. He said it's like the average loss reward, taking the global mean. Now it does the global mean. And it is different. I mean, this thread continues and is very good. So essentially, these loss functions can become very imbalanced, and it depends on your setting. And as we get into these new papers, it's really kind of obvious that the different ways of doing this is largely a stability issue. What we'll see in this Dr. GRPO paper is that they have kind of an extreme statement where they're like, clicking through this one, we scroll down, this is the Dr. GRPO paper, we get more pages. They have this where they're like, all of the GRPO implementations or PPO implementations in open source are actually biased by doing this sum that I talked about. This red line that they have is something that would be called a masked mean, where they're saying that a masked mean is essentially biasing versus like a length bias in GRPO. So it's rewarding long samples. So it says, to our surprise, all these implementations exhibit the per response length bias in the loss, which was present even before the publication of GRPO. So what we're saying is that we have this masked mean where you're dividing by the number of samples on the prompt, which is the way that if we go back to the DeepSeek loss, this 1 over O term has kind of been handled within the open community. I would say that there's very likely a reason that DeepSeek actually does this 1 over O term, but in the math it's not necessarily motivated. So what you could see is that there's actually a theoretical analysis in this Understanding R10 paper where they go through and they do a derivation of what looks like GRPO from the basics of policy gradient. And they pretty much see that the objective 1 over O never shows up. And this is really where the gap between the theory of PPO and the implementation for language models has kind of rubbed together. So if we start at the very basic theory on the left, like this clipping argument, if we're actually to implement it with language models, we need to do this kind of sum over tokens and sum over all of these things. So we have something like this, and we have to sum over them. I think Daniel's example is very good. So we just need to sum over these log probabilities that we get per token when we're sampling from a language model. And the natural thing, if you're working in the field, is to just normalize by the number to create some sort of nice numerical behavior. And the nice part about this Dr. GRPO paper, where they are obviously somewhat spicy and saying like, oh, all these implementations do it wrong, is that they have a theoretical underpinning to it that says that, look, the PPO loss that everybody has been using is really derived in a way that might not be matching the theory. And what they show is essentially in this paper that this dividing by O term essentially biases short correct answers and biases for them, and it biases for long repetitive answers. And removing it is something that they say should help the kind of math of GRPO actually work out. And what this looks like is, we go back to the TRL trainer. Let's see if this goes back. So we need to find the loss. So if we have the loss here, what it's doing is we have the torch.mean, and then loss is equals to this, and this is the masked mean operation, where the second part of this is doing this length normalization. And if we compare to their implementation here, what they have is this masked aggregator function. And masked aggregator, instead of using a masked mean, is doing a masked sum, and they're normalizing by the max length, which is what they say in the paper right up here, where they're like, instead of, let me get to it. Instead of normalizing per the response length here, they're normalizing per the max length of the tokens here. So kind of normalize every possible token in the batch. I don't think that this actually has a huge impact. And I would guess that DeepSeek has considered these things. And a lot of people are have kept this 1 over O term for stability and kind of pushing the frontier of RL literature for language models out over time. And these changes like Dr. GRPO and Dapo are kind of making it so the kind of theoretical underpinning of GRPO matches what we want, but it might be a trade-off of numerical stability, and it's kind of still an open question for if it is going to make everything fundamentally better. So I have a blog post that's coming out on this soon that'll kind of write up this argument in a bit more coherent way than I've gone through. But hopefully this is helpful. I think there's a couple more things to go through in these papers. I think here we're looking at this Dr. GRPO paper with their improvements. The second red point with question level difficulty bias is definitely a great one. So what's happening here is that they're looking how the advantage is computed in GRPO. We can check the original paper here. If we scroll down with GRPO, blah, 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 they have the for outcome supervision, which is what people are doing for reasoning models, they have this definition. And what this Dr. GRPO is saying is that this standard deviation on the bottom is actually rewarding, let's get this right. So essentially questions with lower standard deviations, so either the easiest or the hardest questions are rewarded in this formulation. So the standard deviation measure is looking at how different the answers are across the potential answers generated for a prompt. And in many ways, questions that have a high standard deviation are the highest learning signal because the model gets it right sometimes and wrong sometimes. It's not questions that are always wrong or always right. And what this standard deviation would do is lower the advantage of the samples that have the correct answer, making the learning signal weaker when you pass it into the PPO thing. So this idea of removing this, which is already implemented in TRL, is a really brilliant idea. It just makes it so that the data work done is probably a little bit less important. So a lot of the data work in papers like Kimmy and other reasoning papers that talk about data talk about how a distribution of difficulty is very important. And this could be an algorithmic way that kind of helps address this. And then here you can see this kind of their response bias again. Trying to intuit this is definitely somewhat tricky. So what we can think about is that if we go back to a paper like this that I'm going to publish, is what do we actually want to have happen when we're doing policy gradient? When we have an advantage that is greater than 0, that is positive, that's a behavior that we want to reward, and the kind of vice versa and stuff like this. And this example kind of shows you this is a negative, these are all negative advantages, which is something to penalize. I'll probably switch this around. But what we're looking at is that like this, if you have a short sequence versus a long sequence, the high advantage can kind of have a lower impact if you're kind of averaging per length rather than if you're taking a uniform averaging per all the samples, which makes this surprising token or this useful token more important. So if we think about this last token, in this case, if you were averaging over this shorter sequence would have a bigger impact if you're doing a length normalization than this longer sequence. And with reasoning, we really want longer sequences to be able to happen because that's part of the thing that we're interested in. But with doing naive length normalization, it would actually be the shorter sequence that is prioritized because that positive part of the advantage or the what turns into the log ratio after you do updates in the batch would actually be squashed. And there's other arguments like vice versa, and I recommend you to look at the paper. But really, hopefully some people found my rambling on this useful. I think the other thing that you should know is that there's this other paper, Dapo, which has a lot of similar modifications to GRPO. So what they have seen is that they do this, they talk about removing the KL difference, they have some other tricks. The one that is relevant to this and the implementation is rebalancing the token level policy gradient. So here in red, you can see the change from GRPO and their setup. So let's separate these tabs. I'll move DeepSeek in. So here we can see this, and we'll scroll back up to GRPO. So here's the GRPO loss on the left and what they've changed on the right. So this 1/O term has been moved out, and they kind of moved it out to normalize over the total number of tokens in the batch across all the samples, rather than the number of tokens in one specific response. The reasoning that the Dapo paper gives is very, very similar to the reasoning from the Dr. GRPO paper that I've talked about for most of this. I can kind of quote it directly. Talking about using the per token loss, the authors say that since all samples are assigned the same weight in the loss calculation, all samples being completions to a prompt, tokens with longer responses, which can contain more tokens, may have a disproportionately lower contribution to the overall loss, which can lead to two adverse effects. First, for a high quality For high quality long samples, this effect can impede the model's ability to learn reasoning relevant patterns within them. Second, we observe that excessively long samples often exhibit low quality patterns such as gibberish and repetitive words. Thus, sample level loss calculation, due to its inability to effectively penalize those undesirable patterns in long samples, leads to an unhealthy increase in entropy and response length. The crucial thing to know is that Dapo feels more like a empirical find and kind of a cool trick, where the Dr. GRPO authors did this derivation on the kind of PPO loss to kind of see that this 1 over O term never actually appeared. I don't necessarily love the notation. They should have just showed it and then just said that it wasn't there. Highlighting something in red with an X is kind of confusing. That's just to say it didn't show up. And Dapo, on the other hand, on the right here, is changing the loss function that DeepSeek had on the left to kind of solve these learning dynamics rather than rederiving it from scratch. So they're both great, and hopefully some people find this somewhat useful as a potential addition to kind of looking through all these loss functions and understanding the debates going around on if I think it's this figure is what people are looking at with the essentially says that all open implementations are wrong and how they aggregate is different. I will say in conclusion is that RL and RLHF really didn't care about response length before. So all these implementations were largely niceties. And now where response length is so crucial to reasoning and models can be very sensitive when sampling long context, this response length is more important. So I wouldn't say it's that people were doing it wrong. It was just not something that was necessarily important. And now kind of understanding how the samples are aggregated in this per token loss is becoming interesting. So I find that cool. I hope some of you find this useful. I'm going to post this on YouTube unedited, and we'll see you later with more high quality content. Thanks.